Geotechnical Engineering, Part A, Soil Mechanics, Session 6, Atterberg Limits. Atterberg Test. So this is a configuration of Atterberg Test. And Albert Atterberg is a Swedish chemist and agricultural scientist who developed Atterberg tests, born in March 1846 and died in April 1916. The importance of his work didn't fully recognize. This is a figure of Atterberg. And until the father of soil mechanics, Carl Terzavik, which is an Austrian mechanical engineer and also geotechnical engineer, with the help of his assistant, which is an American civil engineer, Casagrande, who developed and standardized Atterberg test, which is currently available to us. So Carl von Terzavik was an Austrian mechanical engineer and geotechnical engineer and also a geologist. We know him as a father of soil mechanics. He has an Italian origin, and his father moved to Astoria and Graz, and he then studied mechanical engineering at the University of Graz, and has a huge interest in theoretical mechanics. Arthur Casagrande, his assistant, is an American civil engineer of the soil mechanics teaching program in Harvard University in early 1930s, and he is a geology and geotechnical engineer. Has a lot of research in seepage and also soil liquefaction, and he was the one who rearranged the original Atterberg test and provide them to like at the current Atterberg test to us. This is a photo of his office in early 20th century. So let's back to Atterberg test. So plasticity and Atterberg's limits. Fine grained soil behave differently in terms of their physical and visual properties with varying moisture content. So when you change the moisture content of fine grained soil like clay, they behave differently from solid state. They change from solid state to semi-solid to plastic or moldable material, and finally to the liquid one. So those are the Atterberg's limits. So the fine grained soil change from solid to semi-solid, from semi-solid to plastic or moldable, and then to liquid by increasing the water content or moisture content. So an example of them is oven dried clay to then hard clay or less plastic clay, pottery clay, finally concrete mixture just before the hardening. So the point is the boundaries of this variation called the Atterberg's limits. So Atterberg limits talk about these boundaries. So something from solid, boundary of solid to semi-solid called shrinkage limit, boundary of semi-solid to moldable or plastic is plastic limit, and boundary of plastic and liquid called liquid limit. So in Atterberg's limits, air develops the problem, develops the crack. For instance, a soil with a plasticity of 30%, almost 30, but having entrapped air within the sample doesn't have its sufficient plasticity even by 33% of moisture content. The reason is because the air induces crack in sample and reduce its plasticity or moldability. That's why all Atterberg's limits, that's important, all the Atterberg limits should be or are in fully saturated states. So SR is 100% in all Atterberg's limits. That means air percentile is equal to 0. There is no air in Atterberg's limits. Let's talk about liquid limit. As you move from higher moisture content to less moisture content, first limit you pass is liquid limit from a concrete mixture before hardening, which is very moldable. It's just coming to a plastic condition, which is a less moldable for pottery, but still you can shape it easily. And the moisture content that by definition is the percentile of moisture. Then it closes the gap of the groove by the length of 12.7 millimeters, which is almost half an inch, along the bottom of groove after 25 blows in our Atterberg's design machine. By that's the definition of liquid limit. So if the distance is 12.7 millimeters, it just barely close the gap between part of the grooves. That's so a liquid limit is a length of 2.7 distance of soil sample by 25 repetitive blows of Atterberg device, and we reach to, if it closes the gap, that's the liquid limit moisture. Let's define the plastic limit, the second one, from plastic to semi-plastic, from pottery clay to harder or less. That's from plastic or moldable material soil to a semi-solid. So it's going to be harder and harder. So by definition, hardening, handling relatively high deformation in soil without rupture, crumble, or cracking, called plastic limit. In a more technical verb, plastic limit is defined as the moisture content in percent at which the soil crumbles when rolled into a thread of 4.2 millimeter on in diameter. So means if we call it 1, 2, 3, 4, and this is a 80 reciprocate back and forth movement in a minute. So if you work with a sample of soil and it reaches to a diameter of 4.2 millimeters, that's not yet the plastic limit by definition. If it just cracked and crumble, and that's also, we lose our sample in this case. This is not also plastic limit. If it just passes 4.2 millimeters and it just goes forever, that's not also. But if it just goes by a diameter of 4.2 millimeters by definition, and we start to see the cracking, that's exactly the condition of plastic by definition of Albert Atterberg. So again, if diameter is 4.2 millimeters and start cracking, that moisture is plastic limit. We do have a plasticity index, which is the difference between liquid limit and plastic limit. The plasticity index, PI, is the difference between liquid limit and plastic limit of a soil. So PI, plasticity index, is liquid limit minus PL by formula. And let's go to a deeper understanding, interpretation of plasticity index. So it says if we have two sample 1 and sample 2, both of them has liquid limit of 50. The first one has plastic limit of 40 and the other plastic limit of a bit longer for 35. If the normal moisture of both samples are in 45 percentile of water content, moisture content. So, and if in other scenario, if the sample 1 goes by, so that's a identical to each other. But if you move the normal moisture content for first sample to 38, out of plastic limit, and for the other one also go by 38, which is inside the plastic limit. So you can easily see for the second sample, 38% is inside the plastic limit, and for this one it just goes for the other limit, which is a semi-solid condition. So if we want to interpret, if let's make it a bit clean. So in the scenario 1, we have less plasticity clay because it just entered to semi-solid condition. But for the other one, it is still a plastic clay. So if we want to interpret, uh, both of them are located in, let's have a clear-cut understanding of PI. So plasticity index is a range of troublesome moisture domain of soil, which, if the normal moisture content of soil locates inside it, the physical state of soil is loose and moldable. As the PI is larger, the chance of getting rid of it is less. So if we have a larger, so in this case we have a larger plastic limit, PI, plastic index, so we are still in a troublesome domain of soil and we want to get rid of it sooner, like scenario 1 at the top, but our PI is extended in comparison to the top one, which is from 40. This is 35 to 50. That's the physical interpretation of plasticity index. And the final limit is a shrinkage limit, which fine grained soil, when they're losing their moisture content, their shrinks. The moisture content in which the reduction in volume stops called shrinkage limit. So in other words, soil shrinks as moisture is gradually lost from it. With continuing loss of moisture, a stage of equilibrium is reached at which more loss of moisture will result in no further volume change, in this condition. So by reduction of losing their moisture content, so this is moisture content, by losing moisture content, they can easily see their volume of reduction. This is volume, this is moisture content. So by reducing moisture content, the volume is reducing as we finally reach, eventually we reach to a point at 3, which by pushing it forward to the origin, this is our origin, by changing the moisture content, the volume is constant. Volume is constant. So that point is called shrinkage limit. Solve a problem in shrinkage limit in this video. Thank you.